Okay, folks, so before we move to Jonathan's talk, two things. First, I should have said in my introduction before, this is just my self-centered worldview, I should have given just a brief explanation of this institution for people who may not have been here before. So CCQ, the Center for Computational Quantum Physics, is a research division of the Flatiron Institute, which is a research institute, which in zeroth order you should think of as like the Max Planck Institute, fully funded by the Simons Foundation. The Simons Foundation also runs a grants program in various areas, including math and physical sciences. Their grants building is the one directly across the street on the other side of 21st Street. So the Flatiron Institute at present comprises 4 units budgeted for about 50 people each, including scientific staff, postdocs, and administrative staff, plus a scientific computing core whose job is to provide computational resources and the infrastructure needed to use them. So our brief is to do theoretical and computational science of a sort which cannot be done or cannot easily be done in universities. And besides that, each of the institutes has a wide latitude to organize the science as it pleases. So the existing units are CCA, Center for Computational Astronomy, CCB, Center for Computational Biology, CCM, Center for Computational Mathematics, and CCQ, which is our unit, the Center for Computational Quantum Physics. CCQ is directed by Antoine George. I am co-director, and Angel Rubio, who is here, is a distinguished research scientist. We have about 20-something postdocs, 15, 16 permanent staff, a fair number full-time here, and some, including Antoine and myself, shared part-time with universities. And our mission at CCQ, as we see it, is really to do everything that is interesting with the quantum many-body problem in all of its different guises, one of which is what we're hearing about today. So we do research, we organize conferences and meetings like this, as well as smaller, more focused meetings with a higher density of talks. Anyway, so that's a brief explanation of this. And then finally, before I let Jonathan start, I just wanted to say this is intended to be a workshop. Everything should be informal. So please don't hesitate to ask questions during the talk, and we'll just manage the time appropriately. So, Jonathan.
Okay, so thank you for that introduction. I'm going to actually not talk about any of the things that Peter said I might talk about, but I'm going to talk about strong light matter coupling with organic molecules in optical cavities. And I want to start by motivating the kind of questions that I want to try and be able to answer, and then the model that we're going to use for most of this talk for trying to answer those kinds of questions. So we've already heard about polariton condensation, and what I want to really highlight here is a set of questions that these different kinds of experiments prompt. And so if I just think about the experiments that now a decade and a half old on cadmium telluride polariton condensates, at least to me, the kind of questions that I think are particularly interesting is to understand this relation between lasing and condensation, and at a practical level to understand when you get a state, what is it that controls which state gets macroscopically occupied? Is it the energetics of the state and it's the lowest energy one, as you'd expect in a condensate, or is it the dynamics of which mode has the highest gain, and how does gain balance loss? If I move into organic materials, this interest in organic materials in terms of condensation really started with work now 9 years ago by Stephan Keener-Cohen and Stephen Forrest, who saw polariton lasing in anthracene crystals. And this prompts a whole set of extra questions, and in particular, this is really the question I'm going to spend a lot of time on. There are strong vibrational modes that you see in the spectrum of these molecules, and you see that these vibrational replicas seem to play a significant role in polariton condensation. You get condensation more easily when the energy difference between an exciton and a polariton matches the vibrational mode. There are other questions here that come about with organic materials, perhaps not so much with this crystalline one, but other organic materials about the effects of disorder. And there is this question again of lasing and condensation, how do these fit together? Since that experiment, there have been a whole variety of different organic materials showing condensation or lasing, and this then prompts other questions about what happens if this is somewhere between the limit of Vanier excitons of electron hole pairs as in standard semiconductors, or molecular excitations as in simple organic molecular systems. But then you can also start to ask questions, if there is this whole zoo of different things you could put into a cavity, what is the optimal material? How should you go about looking for the best materials to get the lowest threshold organic photon laser? And there are other questions about trying to look for nonlinearities. And just to finally mention in this context, there is also the set of experiments on photon condensate. So these are organic dyes in an optical cavity where there is no strong light matter coupling, but there is still the appearance of coherence, and there is still relaxation towards what seems to be the lowest energy state in the experiment. These are organic dyes in a cavity that show coherent light emission, and so there's an obvious question about how do these relate to a dye laser, and the other obvious question here is what happens as you go between the weak and strong coupling regime. So these kinds of questions motivate what I've wanted to do in this area of trying to understand lasing, condensation, weak coupling, strong coupling, relation to dye lasers, etc. And to answer these kind of questions, this prompts need to think about what kind of theoretical approaches you can make. And I'm going to talk about two approaches I'm not going to take, and then the one which I am going to take. So the first approach I'm not going to take is a kind of approach of trying to include all of the possible physics of the molecular degrees of freedom. And the reason for not doing that is that this is great if you want to understand in detail what happens in one or a few molecules, but these collective phase transitions, this lasing behavior, is generally something you see with large numbers of molecules, and it will be very hard to include all degrees of freedom and go to 10 to the 5 molecules at the same time. On the other hand, I could take the kind of extreme top-down approach of saying, well, then let me look at the equilibrium statistical physics of a Bose-Einstein condensate model or of a laser model. But the problem with that is that it predetermines the answer you're going to get. If I write down equilibrium statistical physics of some Hamiltonian, I'm not going to describe whether it's a laser or a condensate. And similarly, if I start from first principles with laser equations, I'm not going to see the same physics as equilibrium condensation. And so what I'm going to do is I'm going to steal this picture from Auerbach's book on interacting electrons and say that really what I should do is build a toy model of this system. And the idea of this toy model is it should have enough degrees of freedom to capture the physics that I'm seeing, but be tractable to look at the full many-body physics with 10 to the 5 molecules and understand what I see from that toy model. And the toy model I want to talk about here is something that we've called the Dickey-Holstein model. This is based on thinking about a picture of an organic molecule as having some particular strong vibrational mode that couples to the electronic state. And that comes about by saying that there is some relatively soft energy landscape in terms of one particular nuclear coordinate, and that there is an offset between that potential minima for the ground state and for the excited state. And the photon will cause approximately vertical transitions in this, but the coupling to light is faster than any nuclear dynamics, so you'll get this vertical transition picture. And then if I think about these vibrational levels, I can approximate this as a 2-level electronic system plus a vibrational state which I treat as a harmonic oscillator. And this then leads to this Hamiltonian. So this is what we call the Dickey-Holstein model. The first terms in black are the Dickey model, so it's a single photon mode coupled to many 2-level systems. I will later mention Dickey and Tavis Cummings model. This is Dickey in the sense that I have not made a rotating wave approximation in the matter-like coupling here. And the Holstein bit is that I couple each molecule's electronic state to a vibrational coordinate, to this offset between ground and excited states, and there is this energy for the vibrational mode.
But just a quick question. Is it in purpose that you drop the A² term, or does that matter at all?
So I will put the A² term back in later on. Okay. It depends what question I'm asking as to whether I think I care about the A² term. Yep.
Do you neglect any enharmonism?
Of the vibrational mode, yes. Yeah.
But should play a role, because everything will be dictated by the Frank-Condon transition in the molecular system.
So I think it again depends which question you're asking. If you are asking just about the structure of vibrational sidebands, then I'm not sure it plays a huge role. If you start asking about thermalization of vibrational modes from their own dynamics, then it plays a role, but I will actually put in some external thermalization processes. Okay. So with that toy model in hand, what I'm actually going to talk about for 2/3 of the talk will be about this model, and I will first say some straightforward things about the nature of the eigenstates of that Hamiltonian. And then what I want to talk about is trying to understand lasing from that model in both weak coupling and strong coupling, and understand the differences that you get when you add strong light matter coupling. How does strong coupling in that model change the nature of a lasing state? I will then, for the last third of the talk, say something quite different, which is that what I've done in that model is to include all the vibrational degrees of freedom in the system Hamiltonian. And that's just about tractable, but if I want to go beyond that, it would be great if I didn't have to include all of the vibrational physics in the Hamiltonian, but could capture that by some effects of the bath. But that goes wrong if I try and treat the bath as some kind of Markovian memoryless dissipation. And so what I'm going to talk about is a method we've developed recently, which I think can eventually be applied to this for efficient simulations of non-Markovian problems. Okay. So I'm going to actually start by changing the Hamiltonian to now make rotating wave approximation. And I want to ask a very straightforward question in this context, which is, if I restrict myself to the subspace with exactly one electronic excitation, what is the nature of the eigenstates of this problem? And I want to ask that because, firstly, yeah.
I have a question. So you couple the photon mode only to the electronic excitation?
Yes.
But you could also couple it to the vibrational.
You could, there's a whole separate question about what happens with strong coupling to vibrational modes. I think we'll hear more about that later in this meeting. If I wanted to couple, these vibrational modes here are typically much lower frequency than these electronic transitions. So you can either have a cavity which is resonant with the infrared vibrational modes or with the optical cavity modes. And I'm focusing on the case where it's a cavity that's resonant with the optical transition.
But your method could also describe the other case, where you have coupling to both.
So I think what I'm about to say about eigenstates probably could be adapted to that case. I don't know if I could straightforwardly translate all of the results. Perhaps we could discuss that later. Okay. Yeah, so I'm going to restrict myself to the space with one excitation and ask about the nature of the eigenstates. And part of the point of doing this is that this will be a problem which I can solve exactly, or at least exactly numerically, and then I can use that to build approximate wave functions and then understand how I should write approximate wave functions for this kind of system for large N. In what follows, it will be useful to keep in mind that I could also have written this always in terms of the momentum and coordinate of a vibrational mode. And so this is just this electronic state dependent thing is just an offset of the optimal vibrational configuration. And as I said, I will restrict to exactly one excitation. And really the question to ask is, what controls the ground state wave function? What happens as a result of competition between the light matter coupling and the coupling to the vibrational mode? So let me start by just answering that question in the simple case of n is 2 for just 2 molecules, and show you what happens in terms of the Wigner function of the vibrational coordinate. So this is a quasi-probability distribution, and I'm going to actually show this Wigner function for the vibrational state of one molecule conditioned on what the electronic state is. So the left column is what is the vibrational state of the molecule when there is a photon. If I take the ground state wave function, project onto the bit with a photon, the middle column is when this molecule that I am looking at is electronically excited, and the right column is when another molecule is electronically excited. And these two rows are for two different couplings to vibrational modes, and you see these pictures are notably different, and one thing we'll see in just a moment is there is a fairly sharp transition when you increase the coupling to the vibrational modes. What is perhaps most remarkable in this picture is that the bottom left and bottom right pictures are not the same. And what that means is the vibrational state of one molecule apparently knows, even when this molecule is not excited, whether the electronic excitation went into the photon or went onto another molecule. But actually that's not too hard to understand. If I think about the vibrational energy potential landscapes as a function of the nuclear coordinates of molecule 1 and molecule 2, here is the potential landscape when I have a photon. Here it is when I have molecule 1 excited. Here it is when I have molecule 2 excited. And if I take a linear superposition of all of these, this is what the potential landscape looks like for the lower polariton state. This has two minima, and this is what you're seeing here. This elongated blob is the state where you've got some weight in this position and some weight in this position. But when you're in the state where molecule 2 is excited, you bias the system towards the condition where molecule 2 is displaced, and therefore molecule 1 isn't. So you can understand quite a lot about the structure of what's going on in this picture, but this is all for n equals 2. Now, really, we have n equals 10 to the 5 or so. So to go towards that limit, let me now point out that actually this problem is not that hard to solve for medium size n, because I've taken a model where all molecules are equivalent, and I have permutation symmetry. And if I just use that permutation symmetry of the full many-body state, including both electronic and vibrational state, I can extend this to what happens for n is 20. And so some of these features change a bit. You don't quite so clearly see this double blob structure, and that's because now with 20 molecules, I have a potential surface with 20 minima, and in 19 of those minima, molecule 1 is not displaced, and in only 1 it is. And so this gets a bit washed out. But the real point of this is I can solve this problem, and now I know not just the ground state energy to compare to any approximate solution, but I know from these pictures what kind of state should I think about writing down to write down a variational ansatz that might capture that ground state. And the state I should write down is a kind of polariton-polaron ansatz where I have a displacement of the vibrational coordinate, so this d operator displaces the vibrational mode, and I have a different displacement for each state of the molecule. So lambda A when there's a photon, lambda B for the molecule which is excited, lambda C for the other molecules. And what's great about this ansatz is you can calculate a closed form for the ground state energy of this problem. You can in fact eliminate these alphas and betas and just get a function of the lambdas. And then you can think about minimizing that function over lambda A, lambda B, and lambda C. And there are two sort of obvious answers that drop out of this. You find that in the limit of large n, lambda A and lambda C probably should go to 0, and I'll call this thing the entangled polaron ansatz, where I allow lambda B to be arbitrary but drop the other two, and it's entangled in the sense that the vibrational displacement is conditioned on the electronic state. The other ansatz, which have been mentioned in the literature before our work, is to say in the limit where the light matter coupling is very strong, then all of these lambdas should become the same. And I'll call that the product polaron ansatz, where I just have a polaron multiplied by a polariton. And so I can then look at the ground state energies of this one excitation sector problem. Here for n is 10 to the 6, and you see that the entangled polaron always does better, but at very large light matter coupling strength, these two become rather comparable. What you also notice in this is that there is a sharp kind of discontinuity here, and what this is saying is there are basically two states that compete against each other. One is to have the vibrational modes very similarly displaced in all the electronic states, and then to get a very good overlap and therefore large light matter coupling strength, and that's favored at large Rabi splitting or small coupling to the vibrational mode. But the other state is to have the vibrational state quite different and the light matter coupling suppressed, And as you tune these parameters, you get a transition between those two states.
So, excuse me, is this the Polaron transition? Are you saying that there is one, if you just have one excitation, then it gets localized on one side and that side gets a large lattice distortion?
There is a Polaron up to here, and then the kink is when the Polaron basically goes away.
Right, and the other one, it's reversed as I increase.
Yes,
length.
exactly,
Right,
yeah.
okay,
Yeah.
got it. So
Yep.
that is the Polaron.
It is the Polaron transition,
There's a
yeah.
version of that in this.
Yep.
Yeah, okay.
Okay.
Yeah.
So this is results for 10 to the 6. I can't do the exact solution for 10 to the 6, but if I go to 20, where I can do the exact solution, this picture doesn't really change that much. And there I can then compare this ansatz to the exact result of numerics, and what you see is this works pretty well. There is no actual kink in the numerics, and I don't have the slide here, but you can go beyond this ansatz of a single polaron and write down an ansatz with multiple polarons, and then you find basically a perfect match to these numerics. And so what this then tells you is you actually have a test bed to be able to really say what's a good ansatz for this problem. You also find that you can show from this kind of ansatz that in the large N limit, mean field-like approaches become very good. Okay, so now I want to switch to talking about lasing from this kind of model. And I'm now going to put back in the a squared term that I was asked about earlier. So I put this a squared term in, and I'm now not making rotating wave approximation. And I put that in because I want to talk about a lasing transition that is driven because I excite the systems and avoid a ground state phase transition that would occur if I ignore the a squared term in this model. And what I want to do is take this Hamiltonian, but add to it all kinds of incoherent processes. So I will add loss of photons and pumping and decay of the electronic state, dephasing of the electronic state, and processes which try to relax the vibrational coordinate toward what should be its ground state. So this is capturing any non-molecular vibrational modes or sort of long wavelength phonons, or if it's in solution, effects of the solvent, or whatever other physics there is of other lower frequency vibrational modes, relaxing the vibrational mode that I include in this Hamiltonian. And what I want to do with this is to not make any approximation about weak light matter coupling, and not make any approximation about weak coupling to vibrational modes. So both of those limits can be done straightforwardly. If it's weak light matter coupling, I treat G perturbatively, I get absorption and emission, and I can describe a photon VEC. If it's weak coupling to vibrational modes, then it becomes some effective dissipative process just for the true level systems. What I will do as an approximation is use mean field theory, and that's controlled by the fact that there are a large number of molecules per relevant photon mode. And so I will make that as my only approximation, and then to deal with all of this physics of the molecules, I will say that that two-level system plus harmonic oscillator becomes some n-level system where n captures all of these different vibrational sidebands. And I'll rewrite this Hamiltonian in terms of generalized Gelman matrices just for convenience, and this is not particularly important. The main point is what I'm going to do is write down mean field theory. So I write down equations for the photon field and for the state of this matrix. And I will actually just show you results only of asking about linear stability of a normal state. So starting with a state with no photons and asking when do I get a lasing state. And I can do that by linearizing these equations, looking when there's an unstable mode. I will be able to tell what frequency that unstable mode is at, and I'll be able to tell the nature of that mode and then say what is going on in causing that lasing state to occur. So here is a picture which is technically not in the weak coupling regime, but the weak coupling limit looks pretty similar. And what you see here is a phase diagram where the region in black is where it shows lasing, where the normal state is unstable, as a function of cavity frequency and as a function of pump strength. And this is all plotted in units so that the two-level system energy, the bare splitting of the molecule is 1. And so what you see here is there is very low threshold around 0.8, and that is one vibrational replica below the zero phonon line. And that's basically what you expect for, say, a dye laser, that if you tune the cavity to be resonant with the first vibrational sideband below the zero phonon line, you get lasing easily because you can easily invert the transition from the excited electronic state, ground state, to the first vibrational state of the ground state manifold. And that has energy 0.8 because I've chosen the vibrational frequency to be 0.2. On the other side, when you're at the vibrational sideband on the blue side, you get very strong absorption, and basically you can't make it lase at this point until you pump very hard. But now what I want to ask is what happens as I change this light matter coupling strength? And what you see is a rather weird feature where this thing which we thought we understood as being about vibrational resonances somehow extends itself over a very wide range of cavity frequency. And what I want to explain next is where that comes from by looking at the nature of the mode that's causing this. So just to orient that discussion, let me first show the case we understand, and let me show the nature of all of the eigenstates of this problem. So here, these are the frequencies of these modes versus cavity frequency. The grayscale is how much photon there is in a mode, and the pink dashed line is where is the bare photon. And then I can ask which mode goes unstable. So the blue line here is how fast a mode grows, and the yellow dashed line picks out which real part, which frequency corresponded to that mode which goes unstable. And the basic answer here is it is a photon mode that goes unstable. It pretty much follows the photon. You can notice this is technically not weak coupling because you can see a polariton splitting here around 1 where you cross the zero photon line, zero phonon line. On the other hand, if I pump this system harder, what you see is the polariton splitting disappears, and that's very typical that when you start to invert two-level systems, you kill strong coupling, and so you just get that this is simple photon lasing. So now let me show the same pictures for this case where this thing is extended out very far, and what you see in this case is rather different. The mode which goes unstable is clearly below a polariton. It's clearly not just following the bare photon dispersion, but has bent over and is sticking at more or less the frequency 0.8. And as I commented earlier, 0.8 is the frequency that corresponds to a vibrational sideband of the exciton. And what is going on here is that this is lasing over this whole regime because the lower polariton effectively self-tunes into resonance with that vibrational sideband. And so what you see here actually backs up a picture that had been described before our work in work by Giuseppe La Rocca and collaborators, where they talked about a model of polaritons coupled to uncoupled excitons. But here we haven't divided things into different populations. We just see that there is spectral weight of the exciton vibrational sideband that feeds this polariton mode. And what you can also see in this calculation is how this evolves with coupling strength and with pumping. So when you pump the system harder, you start to invert the two-level systems, and that kills the strong coupling, so this polariton mode goes up further, goes out of resonance, and then stops showing this extended region of lasing over a large range of frequency. So the other thing you can answer out of this kind of model is a question with a thing which is often used as the selling point of why build an organic polariton condensate, which is organic lasers are very hard to build because they have thresholds which are significantly higher than the currents you can normally drive through an organic material. And a polariton condensate should have a lower threshold because it doesn't require electronic inversion. But you can now ask, if I change the light matter coupling strength, does the threshold go down? And I have two answers to this. The first answer is yes, it goes down. But the other answer is no, it's not actually that important to be in strong coupling, because if I write down the weak coupling theory of this, this red dashed line almost perfectly matches what you're seeing here. And this red dashed line comes about from a model which is just about incoherent emission and absorption, no strong coupling physics. And why this threshold is going down is just that as you increase the light matter coupling strength, the emission rate goes up, like g squared. But that's only the answer when I chose the cavity frequency to be at the optimal position. If I choose the cavity frequency to be somewhere else, where it's a very bad dye laser, and in particular at 1.2, where it's a terrible dye laser because it has huge reabsorption, then strong coupling really helps and the threshold drops significantly. And this disconnected blob you're seeing down here, that's actually the feature of this previous picture where you saw this thing bend out to the right and you see a sort of re-entrant phase transition. Okay, so that's what I wanted to say about... Yep.
So if I want to think about this in the dispersion picture, if I had a cavity with a detuning which was completely off, then I would get lasing at some finite k value rather than
yes,
right?
So this is actually something we're looking at right now, is to go back to this model, put in the other k modes, let it select its own k. Yes, you would get finite k lasing if you detuned to the red side so that there are those modes. Here it's detuned to the blue side, so it's just a bad laser altogether.
Just one question. How do you normalize your pumping rate? Is that normalized per the system?
This is pumping rate over non-radiative decay rate.
Right, so when you go to the strong coupling, you basically effectively increase the pumping because you have more system, or is it normalized to the cavity, or is it normalized to the, if you want, to the matter content? Sorry,
well,
it's a trivial question.
So we've normalized it to the non-radiative decay rate.
Right, so now because you see, if you think in terms of an experiment,
yeah,
whether you reduce the threshold, usually you would count it on the input energy to the system.
Yeah.
And it matters, of course, how do you modify your coupling to go to the strong coupling regime? Are you sort of increasing the number of molecules, for example? In which case, I guess, if you do that this way, then you would also implicitly increase the pumping because you also increase the radiative decay rate.
Well, so these are per molecule pumping rates.
Right, exactly.
I should say, trying to do this experimentally is probably very hard because you end up changing either the cavity size and therefore cavity frequency at the same time, but you change mode volume, or you're ending up with problems about dephasing or about quenching or so on. So,
no, sorry, it's just, just to clarify.
Yeah. Okay. So at this point, I wanted to switch to talk for the last 5 minutes or so about something
just
complete.
for curiosity, going back to the how the predictions that you have from this model can be transported beyond the two-level system that you are using to describe the molecular, because eventually in this strong light matter coupling, connections to higher levels will play a role, and going, because this is for the low density regime of molecules. If you go to a high density, in which there is an interaction between molecules.
Okay, so I think there's no real fundamental problem with going beyond this simple model while you're sticking in the mean field regime. It will just make the state space that you have to do mean field theory in larger. And actually, the thing which we're doing at the moment to go beyond mean field and ask about lasing in other modes is based on accumulant expansion. I think there's no problem to do that going beyond this two-level system plus vibrational sidebands. Because in effect, all we have is a Hamiltonian for an n-level system. Now, I wouldn't want to make n very large, but within, say, a 20-level system, I think you could make whatever set of levels you want.
And you think still you will get lasing?
I think you would still get a rather similar phase diagram. The details will clearly change. I generally think that if you're in the strong coupling regime, the direct molecule-to-molecule coupling is a very weak perturbation, because the typical bandwidths that you get for delocalized excitons are much smaller than the typical Rabi splittings, which mean that the rate of excitation going from molecule 1 to molecule 2 directly is much slower than the rate of going via a photon and back again. So on that basis, we have never really worried about that term because I can't see it mattering in that limit. Okay? Right. So in the last 5 minutes, I want to talk about something completely different, which is is really just to very quickly advertise a numerical method we've been developing for non-Markovian problems, and to show one example of what it can do. And this method is based on the quasi-adiabatic path integral developed by Makary and Makarov And because I have an English accent, I have to be very careful when I say this is the crappy algorithm. I'm not saying it's crappy. This crappy algorithm is based on considering a system linearly coupled to a harmonic bath. So O is a system operator, B are bath operators, and the bath is quadratic. And what is done in this algorithm is to write down the density matrix at some time t, and to then proceed as if you were trying to write down a path integral, which means inserting resolutions of identity. But the slightly odd thing is that for the system, I will write down discrete resolutions of identity with sums, whereas for the bath, I will write down an integral resolution of identity as if you were writing a coordinate state path integral. And I will keep discrete times. And then the point is that because the bath is quadratic, this integral over the bath is just Gaussian, and so can be done not just in principle but in practice. And that gives you a form that looks like this, that says that the density matrix at the end involves a sum over system states at all intermediate times. And these J's really are doubled indices because there's stuff to the left of a density matrix and stuff to the right, or you can think about this as a Schwinger-Keldysh closed time path contour. And all of the stuff here is effects of the bath correlations. And I'm not going to say what it is, I just want to say that this is stuff that is explicitly known. There are closed form expressions for all of the stuff in here. And therefore, the problem I actually have in order to evaluate this is I should sum over all intermediate states of the bath this very high rank tensor. And this tensor has a rule for how does it grow, which says it grows by this growth tensor B, which includes all of these i's. And so, in principle, this is great because you know this for arbitrary numbers of time steps, etc. But the problem is that the size of this tensor, of course, grows exponentially with the number of time steps.
So, can I ask you a question?
Yep.
So, how is this setup different from the conventional Caldera-Leggett model?
So this fits exactly something that is in the Caldera-Leggett form. What I'm going to try and do is to show a numerical approach which can deal with arbitrary bath density of states, and so it is exactly in that paradigm. Okay.
No, it's a numerical method for solving Caldera-Leggett kind of equations. And the question is just where you actually make approximations in evaluating these things.
Okay. So the key point which occurs here is that you have this very high rank tensor and you want to sum this. And the thing which we wondered about is if you have a very high rank tensor and you have any reason to believe that correlations between the indices of these tensors are not very large, the thing which jumps out immediately is to think about matrix product states. And if you start thinking about matrix product states, you very quickly realize it's even better than you thought, because this B tensor, the thing which does the growth, is really just a tensor network. So the problem you actually have to solve is to take your input density matrix, and then all of these blue squares represent things I explicitly know. These come from the bath correlation functions. And this gives me my high rank tensor, and I should sum over all of these other indices, and that will give me the density matrix at the end. And the way that we chose to proceed with doing this contraction of this tensor network is to think about this in terms of this sequence of boxes. And I'm going to make here an approximation that's always made in crappy, which is to say there is some finite timescale over which I keep memory. So I will neglect stuff that's more than k steps ago. And the point is, if I know how to contract the stuff in the green box, that will give me a matrix product state. And then all I have to do to get the next level is to multiply this MPS with this MPO, and you can use the Stoudemire-White algorithm, and that will give you another MPS for this next time step. And if you know that, actually you can go back and do all the stuff in the green box, because it's basically just the same, but with a slightly odd MPO, which has got one more leg on one side than the other side. So all of this means that actually I can just reuse existing algorithms from tensor networks. And to illustrate how well this works, let me show this for the archetypal spin boson model with an ohmic density of states. What is well known about this is that there should be localization if this coefficient alpha becomes larger than 1. Actually, it shouldn't be exactly 1 because I'm doing this with a finite cutoff, so it should be a bit bigger than 1. this is a big challenge for Quappy, because any finite memory cutoff will mean that you will always forget the initial state, and therefore you will never see localization. But what you might hope is that as you make the memory cutoff big enough, you start to see something approaching localization. But typical Quappy is limited to k of about 20. And I'll show you some results in just a second of how large k needs to be. So this is what we get just brute force time evolving this, starting with a spin up. These blue and orange curves are definitely not localized, they're decaying towards 0. The curves at the top maybe are localizing, maybe not, it's hard to tell. What I've done here is extracted the decay rate of this at late times. So fit this to an exponential decay, and I know there will be exponential decay because I'm doing this with a finite memory cutoff. And what I care about is that exponential decay purely an artifact of my cutoff? And so to see that, let me now look at the extracted decay rate versus 1 over k. So in the red curve, this is at alpha is 1. What you very clearly say is as k goes to infinity, this is asymptoting towards some finite value. It would still decay even if k was infinity. But at the bottom, it's not clear that this is different from 0. So this looks like this really is localizing, and the values of k I need to see that do seem to be accessible here. Just to note, as I say, Quappy is typically limited to about k is 20. This is k is 50, this is k is 200, which is now possible using this matrix product state method. And you can then extract out of this what is the extracted decay rate in the limit k goes to infinity versus alpha, and see that somewhere around here there is a localization transition. These dashed lines are about error estimates from how good is this fit and how good is this extrapolation at late times.
How did you know how to draw the red and blue lines on your middle panel?
So what we did was to look at the limits of what this this fitting would give. So what's the range of extracted values here that are consistent with this data, with some estimation of the errors on these points. Okay. Yeah.
May I just ask, is this similar in any way to Martin Planio's ansatz for doing this? I mean, with this transfer tensor matrix approach?
So I think there are some sense of similarity, and they both involve matrix product states. In their approach, it is always about systematically transforming the bath from a bath into a line. Our approach doesn't ever involve that kind of thinking. So I don't know if the actual structure that emerges in both cases is related. My colleague Brendan Lovett and Alex Chin, who was working with Martin Planio in developing this, are now collaborating on looking at this in this comparison in detail. As far as I can see, they're not the same thing. But maybe there is some deeper underlying link other than just the fact that both use matrix product states. Okay. Yep.
I'm a little confused about the last plot here. So
yep.
This is the extracted asymptotic gamma versus alpha.
Yep.
You know, the one on the right.
Yes.
And localization transition should correspond to gamma equals 0, right?
Yes.
So the threshold, in the end, there is a threshold in alpha, which should be at 1, or
it would be at 1 if omega c were infinity.
Oh, I understand.
Yeah.
Okay.
And for the value of omega c that we use, if I look at the one loop NRG calculations, the leading correction would say that we should have about alpha is 1.25.
But so the true asymptotic curve should have a breakpoint, right? Or
yes.
So
should have gamma equals 0, or alpha larger than some threshold.
So we did not. So I'd be interested to discuss this further, because we didn't find a clear statement in the literature about what this curve should do as a function of alpha, and I saw some things which strongly suggest actually this should have a essential singularity behavior where all gradients go to 0 rather than a discontinuous behavior. Whereas if we look at the subohmic spin boson model, it should have a discontinuous behavior. So we are looking right at the moment at the the subohmic case, because hopefully that allows a much clearer behavior of discontinuities of this curve. There is clearly no evidence for discontinuity in the numerics we're seeing. And I think that might be what we expect, but if you know otherwise, I'd be interested to discuss.
I actually don't know, but I'm interested all the same.
Yeah.
Yeah, let's discuss.
Okay. That was all I wanted to actually talk about, but I want 1 minute to say something about future directions on this. So, as I already mentioned, one thing we're looking at with the first two problems is to go beyond mean field theory and to look at the fluorescence spectrum and to ask about thermalization of different photon modes in this problem. One question which these non-Markovian methods is I think are very important for is whether the effect of strong light matter coupling should in turn affect the thermalization of vibrational modes, and how should I really think about that thermalization process? And that's clearly not something I can properly do with a Lindblad master equation. Ultimately, there's the whole question of how do you optimize the Lazing threshold and what are the optimal parameters. And I think some of these methods may also then be relevant for questions in the context of Platon chemistry and manipulating the energy landscape. But I also wanted just to mention very briefly that actually the same kinds of problems I've been thinking about here are also relevant for experiments about cold atoms in multimode cavities. And we'll hear more about this later from Benjamin Lev, where you can use the cavity to engineer novel phases of matter. And this is very clearly a problem where you have to go beyond mean field theory, because you can tune this into a regime where the cavity modes are degenerate, so there are many relevant cavity modes. In most of the Platon physics, the number of relevant cavity modes is typically small. And so you can ask about applications of this in distributed computing, memory recall, and whether you can use this to simulate interesting correlated states of matter. So just to mention the people who were involved in the work that I talked about, this Dickey-Holstein model, we first wrote down actually in a paper with Peter Littlewood and Sahina Reja and a former graduate student of mine, Justina Swick. The work about the Platon eigenstates was done by a former postdoc, Asen Zeb, along with Peter Curtin. The work on the Platon lasing was done by a graduate student of mine, Artem Strashko, who will in fact be moving here in the fall, along with Peter Curtin. The work on tempo, this numerical method, was done by a colleague, Brendan Lovett, and his graduate student, Aidan Strathern, my graduate student, Danius Kilder, who will be moving to Caltech to work with Garnet Chan, and also with Peter Curtin. And the ongoing work about going beyond mean field theory is being done by a postdoc, Christine Arnadotter. So let me put up the things I talked about, and thank you for your attention.
All right, so we had some questions during the talk, but we have time for a few more if there are. Yeah.
Is there a notion of a temperature to your bath in this simulation? So bath is assumed to be at a certain temperature.
Which simulation you?
I mean,
the lasing.
No, the last one.
It is zero temperature in the sense that it's just a bath that you're decaying into. So we can do QAPI with finite temperature baths. So it's certainly possible to do all of that same physics works with finite temperature, but the standard subohmic, standard ohmic spin boson problem we were trying to compare to has a zero temperature bath.
It's just, the reason I'm asking is that in the usual Calder-Leggett model, so you can kind of integrate out the bath and end up with the dissipation kernel, and it has ohmic dissipation only if frequency is smaller than temperature.
Yeah.
So if temperature is zero, you actually, I don't even know if one can.
Well, so temperature being zero means that you take this hyperbolic cotangent to just be 1.
Right, but it's basically quantum field theory. It's not really. Anyways, we should maybe discuss.
Okay, so other questions? Just, if I could ask briefly, I mean, I think you basically said this, but just so. How far can you generalize your tempo method? I mean, you know, the problem with the Macri stuff was that you could never get to big enough K to be useful. And now, for some particular class of problems, you can get to much bigger memory times, right? So what range of problems can this work for? Is that?
So I can say I guess, three things to answer that. So in terms of what K we can get to, we went up to K as 200 for this spin boson transition. We can go to much larger K, but probably only in cases where it wouldn't help us. So the sense is, the thing which limits K is still the memory, and you have a much more efficient form because it's compressed into matrix product state. The matrix product state will compress very efficiently if the correlations die off significantly with time. And if they do die off significantly with time, you can make K huge because there's more or less no content. So we've done things with K as 2000, but it wasn't really useful. K as 200, we could go all across this transition. And what we actually find slightly, well, we don't fully understand this, the largest memory size we need, you might have thought is near the phase transition. But actually it seems to be near the Toulouse point, where it goes from oscillating to non-oscillating. And as you go near the phase transition, the memory is not actually that big. We have then used this kind of approach for doing things with very highly structured density of states and comparing that, well, either using models where for other reasons we know what the answer is, or my colleague Brendan Lovett has a paper on the archive this morning in that kind of spirit with two systems in the same bath. So you can do very highly structured densities of states. The limitation, I think, that's still here, which we're working on, is we're still limited by the size of Hilbert space of the problem we put in. And that's something where the obvious, I'll say the obvious thing that we're doing, which is, can we do matrix product states in space and in time at the same time? And the answer is that, well, there's code that currently works, but it's not very efficient, and we're trying to understand why.
Okay, great. No, that was my question.
Yeah.
How bad the spatial structure?
Yeah.
Okay, yeah.
Maybe I missed, but when in your Photon lasing and your Hasti Dickey model, you basically can change the coupling via either the number of oscillators or the ratio of your little g to the coupling to the phonons. Have you done that? I mean, because I would expect, from the experimental side that it would make a relatively big difference in qualitative behavior. Was that, did you look at this?
So within mean field theory, there is only one parameter g root n, and n does not appear separately in the mean field theory. N is the parameter which controls whether the mean field theory is good or not, but within mean field theory, there's no distinction. That's one of the things which we can explore going beyond mean field theory, because there is now a separate parameter which is almost n. To be precise, it's about density of emitters in units of a characteristic density scale. So beyond mean field theory, we can start to answer that question. There we haven't tried to systematically explore that because we have mostly kept ourselves within the range that most experiments are in, rather than saying what happens if you go to really low density of emitter limits.
Okay, so with that, let's thank Jonathan again.